So the talk is about a simple model of ADS-CFT. Joe, Eric, and I constructed a very simple model. The idea is that bulk locality and bulk causality require the CFT to do things which seem somewhat remarkable. And our goal was to construct a simple model to try to achieve this, to see what ingredients were important for achieving some of these things, and then hope to extract a general lesson which would be valid for the actual full ADS-CFT. So that's what I'll be talking about. Before I start, I wanted to very briefly review an old paper by Polchinski, Susskind, Tombus, which introduced precursors, just in order to place the talk into context. So this is Polchinski, Tombus, 99. And they considered the following experiment. So they said, shoot two particles in from the boundary, but aim them so that they just miss. So I can't draw it on the picture, but they go in from the boundary, and then they almost hit, but they don't, and they miss. And then they come out back to the boundary. So then they drew a picture on the boundary of what expectation value of T mu nu looks like. So this single particle propagating expectation value of T mu nu was worked out by Gary and Itzaki, and it's a thin shell of energy. So this particle, as it moves out, there's an expanding shell. So here I'm drawing the boundary sphere, and there's this expanding shell of energy as the particle is moving in. There's similarly an expanding shell on this side. So if we evolve time, so this is the picture around this time when the particles are just about to hit. Then they hit. Can people see the bottom, or should I? I'll go to the top. So time is flowing like this. Anyway, then the shells. That's right. I won't have time to review that. Then the shells, the particles pass each other, and the shells of energy just pass each other, and then they move out back to the boundary, back to the point. So this is at this time, and when the energy is just at these 2 points, is at this time. Now they said consider something analogous but slightly different, where you aim the particles so that they do hit. So just very slightly change how they go in. So now they hit, and imagine they form a small black hole, which then evaporates into Hawking radiation, let's say S waves. So now there's a spherically symmetric wave of the Hawking radiation going out. And then they said, okay, well, let's once again draw expectation value T mu nu on the boundary. What the stress tensor looks like in the CFT throughout this process. And the pictures, all of these pictures are identical, all of them, except the very last one. The very last one is different. The very last one, this S wave hits the boundary, and the whole boundary lights up with energy, homogeneously distributed.
I have a small comment about this. So, you correctly discussed the expectation value of the stress tensor, but the fluctuations in the stress tensor are much larger than this expectation value. So its expectation value is of order 1, and the fluctuations are of order n. So everything you said is fine, but we shouldn't really think that there was this thing that was dark and suddenly the expectation value was good. There's something very fluctuating, and there is a tiny little change in the fluctuation.
Exactly. Indeed. And so what they wanted to do was they said, okay, this is a strange property in the field theory. So what property of the field theory allows this to happen? So they said this is actually possible in a quantum field theory. It's not possible in classical field theory. This apparently superluminal transfer of energy is possible in quantum field theory, because in a quantum field theory it's okay to have negative energy, sort of if you have positive energy compensating later. And by how much it's okay to have negative energy, there are various things that Ford and collaborators have worked out. But this was the basic idea. And so the lesson that I extract from their paper is they took something that's obvious in the bulk. It mapped to something remarkable, what seems remarkable in the CFT. And then they gave a one-word explanation of why it's possible. They also did some calculations where they took a free field model of the boundary and showed that squeeze states have these properties. So the goal of the talk will be to imitate what they did, but for a slightly different puzzling bulk. Slightly different bulk feature, which is obvious in the bulk, but puzzling from the field theory. So that will be the talk. So they said more. They said, suppose I'm a CFT observer at some time, say here, and I want to know which picture is correct. Is it this picture or this picture? In other words, did the particles collide or not? What property of the state do I need to measure? And the statement was, measuring expectation value T mu nu will not tell you if you have this state or that state. But they said there should be something. There must exist some CFT operators which do tell you if the particles collided, sort of at intermediate times. And these they called precursors. And so what is a precursor? Well, if we knew the CFT dual of a local bulk operator, for instance phi, then we could measure whatever that thing dual to expectation value of phi is, say around here, phi at this time, this point, and then we would know if the collision had or had not happened. And so let's, for the purpose of this talk, the dual of this local bulk field is what I'll call the precursor. All right. So then the question is, how does one find the precursors? Which is what Dan collaborators have been doing. So let me just briefly review how one finds it. The idea is, as Dan discussed, one uses bulk equations of motion to do sideways evolution. So one evolves in the radial direction to represent this local bulk operator in terms of local bulk operator smeared over this region, still in the bulk but close to the boundary. Both sideways. So this is. So at this stage, after one does this, one has the things Dan was writing down. One has the local bulk operator expressed as the local CFT operator smeared over space and time on the boundary with some smearing function k. So then step 2 is to use CFT equations of motion to rewrite this as an operator at a single time. So this is the step that no one ever does for obvious reasons. So in our model, since we'll take the boundary theory to be free, we'll actually do this step, and it will be instructive.
Are you going to say the one word at some point? I'm curious.
The one-word answer?
Well, you had a one-word explanation.
Yeah.
That was promised.
That comes at the end. I can give you a hint. It's contained in the title. Because their one-word explanation was also in there.
It might be an anagram.
Maybe I should go back over there. Okay, so I finished reviewing Dan Kabat's talk. Now let me review the first part of Dan Harlow's talk.
Vladimir, you know that gauge invariance is more than one word.
So is negative energy.
Two mistakes don't cancel.
We'll see that this afternoon. So let me now say what. So two properties that the precursors must satisfy. And so here, these precursor operators, they are, as the program goes, constructed perturbatively in 1 over n around some background. So they're not non-perturbative operators, perturbatively in 1 over n around some background. And so two properties are the two that Dan discussed. So the first one, they're both obvious from the bulk, but surprising from the boundary. The first one is, if we just look at a single time slice of the bulk, a local bulk operator here should commute with a local bulk operator here, just by bulk microcausality. So but a local bulk operator here is just O in the CFT. And doing this for all the points, we conclude that phi commutes with all local CFT operators. So here I'm just in a single time slice, and by all local CFT operators, I don't really mean all local CFT operators, because from the bulk it's obvious that if you add a particle, it adds energy, so phi will not commute with the gravitational Hamiltonian, so it won't commute with the stress tensor. And as in the Kabat-Lifshitz construction, one can make it so it's just at one point, where all the energy is concentrated at one point, but the second property is again one that has been discussed already for 2 days, which is there are many different ways of evolving sideways. So this problem that is being solved, it's a differential equations problem, but one with time-like data instead of space-like data. And so in particular, the way Dan Kabat was doing it, he was using a global smearing function. So to reconstruct the bulk field here, he used data on this whole portion of the boundary. There's, in fact, other smearing functions, again, which were constructed by Hamilton, Kabat, Lifshitz. These are the Rindler ones. So consider the past light cone of this point and the future light cone of this point. He draws like this. So here we have a bulk wedge, and consider a bulk point within this wedge. And the statement is that one can reconstruct the field anywhere within this bulk wedge using data only on the corresponding boundary wedge, which in this picture is half the boundary. So now doing step 2 and using the CFT equations of motion to evolve to a single time, this means we can represent the local bulk operator here. Let me put it here. In terms of a CFT operator smeared over this region. We can alternatively, by just using a different bulk diamond, which still contains the same bulk point, represent it in terms of a CFT operator smeared over this region, and so on. There are many choices. And so we have this surprising thing that we can write the same bulk operator as many different CFT operators. I say different because they have support on different regions, so they can be both different. But since we only have the same bulk operator of the field at this point, they must all somehow be equivalent. So those are the two properties. There are obviously many more, but these are the two we're going to focus on. And so we'd like to understand what in the CFT makes this possible. So we'll do a model of ADS CFT where we take the boundary to be free. But before doing this, we're just going to make some stuff up and just write down a very simple thing just to try to satisfy these two properties and see if we can do it. So this will be our three-side model. So in effect, we're going to model the boundary as three sites. So perhaps you shouldn't take this too literally. And at each site, we're going to have a field and its canonical conjugate. Really, we have n fields at each site. I ranges from 1 to n, because we're imagining we have an ON theory. We have an ON theory, and what we're going to require is that all physical operators be invariant under a global ON rotation. So again, A is the index of which site, so A ranges from 1 to 3, and I is this ON index. So in effect, we're just imposing the singling constraint. So what are the gauge invariant operators? They're easy to write down. So we have phi dot phi. Phi a dot phi a, so the dot product will denote a sum over the gauge index I. We have phi a dot phi a and phi a dot phi a. So this is a complete basis of gauge invariant operators, basis of local gauge invariant operators. And so to satisfy property 1, we need to find some operator which commutes with all of these for each site. So to do that, let me consider the following operator, LA ij, which will be phi ai, phi aj, minus phi aj, phi ai. So we can easily check that this commutes with all of these guys. Now this isn't gauge invariant because it has these ij indices, but let me now consider the bilocal TAB, so it involves two sites A and B, and I just contract these two L's. So this bilocal.
as a basis for all local gauge invariant operators? I mean, you said something about your theory being free, and if I take 2 time derivatives, that would imply that that's like taking some space derivatives.
Oh.
So are there also ones that are local because they're second derivatives in time, but that mix the sites?
You're getting too advanced. So this isn't, the free theory will be a little later, where it'll be a continuous theory. Here it's just 3 sites. You're not allowed to take spatial derivatives because that would be non-local, since there are only 3 sites.
So that's by definition the complete list.
That's right. Good.
Multiply them. Yeah.
Good. So this guy.
I can't take phi A dot phi B or something like that.
Wouldn't it be more reasonable to impose the gauge symmetry locally as opposed to globally?
No, I'm going to impose it globally.
This is sort of if you impose it globally, there are other global invariants, like phi A, phi B.
Yeah, that's not local.
This is sort of motivated by BFSS theory, where you just have the global constraint. But it's the simplest model that has these properties.
You can imagine there's a Chern-Simons that you took the large K limit of or something.
For example.
Do this as local.
By local, you mean the unitary ON transformation of each that depends on A? It doesn't depend on A.
The gauge invariance I'm requiring is one that does not depend on A.
So why isn't phi A, phi B?
Gauge invariant?
Gauge
It is. It's just not local.
It's not local. Those are the local gauge invariant operators.
local under what?
Meaning they involve one site.
Moving on one side.
I'll get to the continuum.
And why are we restricting to local gauge invariant operators?
Because the property we had here was that the bulk field deep in the bulk commuted with all local gauge invariant operators.
In ADF CFT, wouldn't we also conclude by bulk locality that bulk operator commutes with Wilson loops on the boundary?
We would.
Okay, which are non-local operators.
That's correct. So that connects with property 2. Which one we get to now. Okay. So this is by local. It commutes with all local gauge invariant operators, where that just means these guys and right. And it clearly does not commute with all operators, with all local operators, because it doesn't commute with the ones that aren't gauge invariant. You just try phi, for instance.
Well, more importantly, it doesn't commute with gauge invariant operators that aren't local.
That's fine. Yeah, sure. I was just drawing this distinction of which local ones it commutes. Right. So that's property 1. Now, to get to property 2, let me write down this guy, Lij. So Lij will be the generator of a global ON rotation. So it's the sum of La Ij over the sites A. So this just so this L guy annihilates all gauge invariant states by construction. And so in particular, if I contract it, this Lij with L2ij, let me just write out what this is. So Lij is just L1 plus L2 plus L3. And using my definition of P's, I can write this as P12 plus P22 plus P32. But this is gauge equivalent to 0 because L annihilates all gauge invariant states. And so if I move this guy to the left-hand side, I have an interesting equation, which is that P12 is gauge equivalent to minus P22 minus P32. So the equation is interesting because the left-hand side involves site 1, but the right-hand side does not.
Sorry, the argument is L annihilates gauge invariant states.
That's right.
But then why does this product annihilate gauge invariant states?
Well, these two commute.
Okay.
So L annihilates the state, and then you can multiply by anything.
Okay.
So this is sort of like property 2.
Well, and this is an exact operator statement. It holds on your entire Hilbert space.
That's right. But we do only have 3 sites. So, that's right.
Was that important?
Was what important?
That you only have 3 sites? Why
No.
can't you?
No.
Okay.
But I mean, I'm not including lots of things like spatial derivatives. So what I'll do next, if there are no questions, is a continuum model, just a continuous, basically a continuum limit of this. Okay, let me do that.
Well, maybe it's worth commenting the difference between this and what I said is that, so here, this is again achieved acting on a subspace of states. The difference is that here it's claimed that all physical states are in the subspace, whereas I said there were physical states which weren't in the subspace.
Yeah, so are you going to be able to accomplish this in the continuum model, or?
Perturbatively in one. So I'll construct the precursor to leading order in 1 over n, and I'll achieve it to that order. And then the claim would be that one could, if one continued constructing the precursor to all orders, then one would achieve it order by order. But today I'll only be able to do the first order. So this is going to be the free ON in ADS 3 CFT2. N to leading order in 1 over n.
Sorry, this is probably a dumb question, but the bulk is not large radius, so what
Good.
causal properties is it supposed to have?
N will be large, but it's true that it's a free ON. The reason this will work is because the leading term in 1 over n, and even the leading term only probes 2-point functions, because at leading order everything factorizes into 2-point functions. And 2-point functions are fixed by conformal invariance. So you can take any CFT and this will work.
Okay,
If I were
but you're not using a bulk causality argument per se at this point. Since is there a way to do that?
So to leading order, the bulk field will be free. And so I'll just still do what Dan did and solve the free-way.
But this part 3 could be a big string size. I mean, which
that's correct. That's correct.
Commutator story is not so clear.
Yeah, how do you tell that the commutator should be 0?
Good. So if one went to order 1 over n squared, then it would no longer be true that fields close together commute. I'm not going to go to 1 over n squared. If one were to continue going to higher orders, then I think a true statement would be that the bulk field at the center still commutes with the bulk field far away many radii away, because theory is still sort of local on ADS scales, but I'll stop at leading order 1 over n, so I won't get there. So I just take a free bulk field. So phi of t rho theta, and I expand it in terms of normal modes. So just the standard thing. So the normal modes, I'm calling those J, R, L. The non-standard thing is that the creation operator I'm calling B instead of A. So L is the angular momentum. R is the radial quantum number. So this is the creation operator, or really the annihilation operator, but good enough. Right. So in in this model, the boundary operator dual to phi. So when you take phi to the boundary, this rho goes to infinity, then you get O. And in this model, we're going to take O to be 1 over square root of n, phi dot phi. So that's our dictionary. So just what I'm doing here is as I'm doing this procedure of using bulk equations of motion to evolve the boundary and then using CFT equations of motion to evolve to a single time, but it's easier to do it in momentum space, which is why I'm just expanding in terms of modes in the bulk. So since these boundary fields phi, little phi, are also free, I can also expand them in terms of modes. Like this. So the alpha n is the operator for left movers. The alpha tilde is for right movers. Since we're in 1 + 1 dimension, everything splits into left and right movers. So alpha n is, so for n greater than 0, it's the annihilation operator. N is the momentum. And n less than 0, it's the creation operator. And this is for left movers. And the same for the right movers with tilde. Right, so this I evolve, well, this equation combined with this equation combined with this equation, and a few lines give the following interesting result. U omega L equals 1 over square root of n, alpha omega plus dot tilde omega minus. So here omega plus minus, omega plus minus L over 2. So the equation is interesting because, so this is that I've solved for the precursor because I've expressed the bulk operator which creates a particle of frequency omega and angular momentum L in terms of the CFT operators. And if you wanted the local bulk operator, this phi, then just use this B and plug it into here, and that's the local bulk operator expressed in terms of the CFT operators at the same time. The equation is interesting because, on the boundary, this is a left mover of momentum omega plus, and a right mover of momentum omega minus. So it's like we have two particles dual to a single bulk particle, whose energies, the energies of these two constituents, add up to the energy of the bulk particle, and the difference in the momenta add up to the angular momentum of the bulk particle. Really, it's not two, but many, and because there's a dot product, superposition of various two.
I'm sorry, I'm confused. The bulk field is free and the boundary fields are free?
That's correct.
And that dynamics is consistent?
At this level, it is.
What does at this level
So
mean?
The leading order in 1 over n.
It's because
Alpha.
the constraint.
So alpha is just a creation operator?
That's right, for phi.
So how do you get a bilinear creation annihilation operators behave like a single creation operator?
How do I get it?
I mean, if I just commute B with B dagger.
Good. So let's compute this. E omega prime, L prime. So if you compute this, so to compute this, we're going to use the commutation relations for the alphas, the alpha dagger, and we're going to try to recover the commutation relations we expect for B's. And when we do this, we almost succeed. We get a delta function, which is what we wanted, plus 1 over n times an operator that has two alphas. So we get precisely what we wanted. So the fact that these B's commute up to, or to have this commutation up to this 1 over n, means the same thing carries over for the phis and the pi's and the bulk. And so it's exactly what we wanted. It's a local bulk field up to this order in 1 over n.
So the thing multiplying the 1 over n is some operator.
That's right. It
You
has
say
two
in states close to the vacuum is order 1?
That's right. This operator is normal ordered. Exactly. So if you're close to that vacuum, it's small. And for some sufficiently excited states, it becomes large. And that's precisely what it means for precursors to exist perturbatively in 1 over n.
So you agree with Daniel then? You're just doing...
No, but it was...
You're
in
in some class of states.
But the class of states was known ever since the day precursors were introduced. Precursors exist around any background, perturbatively 1 over n. And then there's perhaps a question if we need to reduce that class of states or not. And if we don't need to reduce it, then what property of the CFT allowed us to achieve those two properties? I outlined, and the struggle is to identify that. So let me just plug this back into here. So F phi little theta HMN. So HMN is just some new function I defined. It's very simply related to these J's. But all I did is I just plugged this into here and then redefined the indices and got this formula. So it's perhaps instructive to rewrite this formula in position space. So these alphas, they're just the modes of the phi. So I can invert this thing and write alpha in terms of phi and pi. And so what I get is smeared by locals. So it's just bilocals phi dot phi and pi dot pi smeared over the boundary. To draw a picture. So here's the bulk field here. And we've represented it in the CFT as bilocals smeared over the whole boundary.
What is it? F of 2?
There's some functions. They're sort of similar to like the Fourier transforms of these H's. We didn't actually work them out.
Could you explain that picture a little more with the various segments on the boundary?
Good. So the x denotes a phi. So I'm presenting phi of theta prime dot phi of theta double prime as an x of theta prime,
yes.
An x of theta double prime. The f is some weight. And then I have an integral over all these possible bilocals.
So an operator is just one segment.
An operator is a superposition of these bilocals.
So those are all examples of the bilocals you're replacing.
Those are examples of the bilocals that appear in this sum.
Okay. The fact that you drew 1, 2, 3, 4, 5, or so on is not really...
Yeah, that's not relevant. Sorry, I was just trying to illustrate this picture. It's just a bunch of bilocals, but of various sizes, centered around various places. So bulk operator is dual to smeared bilocals. So now we need to address the second puzzle. The second puzzle was the fact that, so here I was implicitly using the global smearing function. I expanded the bulk field in terms of the global ADS modes, these J's. I could have just as well done the same procedure but used the ADS Rindler modes. Yeah. That was this wedge. So it's the exact same procedure. So I expand the field in terms of the modes. The thing that goes here is the ADS Rindler modes. This is the ADS Rindler creation operator. And I follow this procedure, and I get almost an identical equation to this, except now the alphas are Rindler creation and annihilation operators. So the Rindler creation annihilation operators, so they have support on this half of the boundary. These alphas. And H is again some function which is related to the ADS Rindler modes. And so now we can try to address the puzzle. So we have the same bulk operator, but we have, that's the left-hand side, but the right-hand side we have two different expressions. This guy has support on the whole boundary. This guy has support on half the boundary. So somehow these must be equivalent. So that's what I'd like to show now. So the thing we need to remember in analogy with what we saw in the three-side model is we have gauge symmetry, this global ON rotation. So Lij annihilates all gauge invariant states, and we can use that to form lots of operators that are gauge equivalent to 0. So let Aij be any operator in the adjoint of On, these two commute in, and this is gauge equivalent to 0. And so the idea will be to take some of these operators that are gauge equivalent to 0 and add them to this global precursor to reduce its support to only that half of the boundary. So then the question is which guys should we actually add? At this order, it's actually easy to see what to add. If you consider alpha m tilde with mn less than 0, then this is gauge equivalent to 0. This is easy to see, so mn is less than 0. That means one of these guys is a creation operator, the other is an annihilation operator. So for instance, the left mover is creation, the right mover is annihilation, or vice versa. So since we're at infinite n, or leading order 1 over n, all correlators factorize into 2-point functions. Now, if you change the operator by adding this annihilates the vacuum on the right, because these guys commute, and one's an annihilation operator. It also annihilates the vacuum on the left for the same reason, and therefore this is gauge equivalent to 0. This is actually a special case of that particular Aij, which I can show. And so this is going to be the idea. So the point is that in this smearing function, in this global smearing function, we can modify this HMN that appears here. We can modify by any function lambda mn as long as mn is less than 0. And all of those things are gauge equivalent.
Do you think you could generalize this statement to perturbatively in 1 over n? So you here at leading order, exactly. You have an operator that's gauge equivalent to 0, You think that's going to keep being the case?
Good. So indeed, so one concern, if we didn't know about this, one concern might be that this is something special at infinite n. But the point is that at any order in 1 over n, we can still construct a large number of operators which are gauge equivalent to 0. So the assumption is that next order in 1 over n, we could add some alpha to the 4th term to this guy, which would be gauge equivalent to 0, and we could still show that the two precursors are equal. Though we haven't done that, but it seems possible.
Vladimir?
Yes?
I'm not sure I understand why you're saying it's gauge equivalent to 0 as opposed to it's just 0 and 2-point function. Like, why are you using the word gauge?
Because that's the word of the talk. That's just one word.
So at infinite n, so at leading order in 1 over n, all the correlators factorize into 2-point functions.
Right, so it's 0 in that sense, but I'm not sure why.
At leading order in 1 over n, it's gauge equivalent to 0.
But why are we saying gauge equivalent to 0? It's 0 in these 2-point functions. Why?
Good. So if you take a state that's not gauge invariant, so if you take a state where you act with a single alpha ni on the vacuum, so then this would not, acting on this state, this would do something. So it's only on gauge invariant states that it does nothing.
Here it doesn't seem that it's that important that it's a gauge variant state. It's just that it's not the vacuum, right? I mean,
Not sure. Let's go back to this.
It'll kill anything gauge.
Well, no, I think you can
No,
argue
it'll kill the vacuum.
I think you can argue that this combination, I mean, you did argue in your paper, I think, that this combination can be written in some way as a function of the generators of the gauge transformations. And then so
This guy. Good. So you want me to write this guy in this form? Is this what you're asking?
Yeah.
I can do that. Right, is that what Douglas was asking?
The question is, it kills the vacuum, right?
That's right.
That's what you're using.
That's right.
Not that it kills other states.
But it does. It kills other states where you act on the vacuum with the gauge invariant operator.
Well, that's not obvious, is it?
From the first line it is, right? Because, right, Vladimir?
That's right.
But if you show that the second line is an example of the first line.
Yeah, that's right.
Yeah,
It is. So let me show that since there's a question. So if you consider Lij and M, so Lij is the same Lij, the generator of Owen rotations. So you can express this in terms of alphas, like in Joe's book. And then, let's see, alpha M. So take this to be Aij, alpha Mi, alpha tilde Nj, and then commute this guy over once. Then you get alpha M, Lij,
Okay, thanks.
alpha n tilde j, minus n minus 1, alpha m dot alpha n tilde. So this guy has an n, so you can drop this guy.
But wait, so now it's not that it's exactly of that type. It's that, I mean, it's
Leading
again
order,
this 2-point function statement, right?
At leading order in 1 over n, but that's all I need. I only constructed the precursors at leading order in 1 over n.
But then it's not clear to me that this gauge invariance is relevant at all. Like,
Good. So let me get to that in a second. Anyway, just right. So this alpha m dot alpha n tilde is what I want. This guy, and this is the Aij. So then you could ask, this wonderful equation got erased. So you could ask what we would do at next order in 1 over n. So at next order, so there are two, in the construction of Dirac does, there are two options to construct the precursor to next order. One is you use the interacting equations of motion, the 1 over n piece, or the other option is to use bulk microcausality. I think effectively we only have the second option since we don't really know the bulk equations of motion. The expectation is that there will be, though we haven't worked this out yet, the expectation is that there will be an alpha to the 4th term, something of order alpha to the 4th, that has a 1 over n to the 3 halves. So it's 1 over n suppressed relative to this term, and it has 4 alphas. These could be alphas or alpha tildes. And so this would be the precursor 1 more order, and then this gauge freedom I would correct by adding something 1 over n with, again, 4 alphas. I expect. Certainly, there's a lot of things I can create at any order. Okay, so let me, it's actually non-trivial that even with this freedom that I can show these two things are equal. So let me quickly show that. So I want to show that this freedom is enough. So the way I'm going to do this is I'm going to take an ADS-Rindler mode and write its corresponding Rindler precursor using the Rindler smearing function, and also write its global, or really Poincare precursor, and show that with my gauge freedom, that's enough to show that these are gauge equivalent. So this guy will have support on half the boundary, this one will have support on the full boundary, and they're both going to be dual to the same Rindler creation operator. So the way I'm going to proceed, so first I write the Rindler precursor, so this is easy. Just omega plus r, alpha tilde omega minus r. That's just this equation I was writing here. So that completes this step. Let me go a little further and do a Bogoliubov transformation on the boundary to write this guy in terms of Minkowski creation and annihilation operators. So I'm going to do a boundary. So gamma here denotes what's usually called both the alpha and beta terms in the Bogoliubov coefficient, depending on if mu is positive or negative. So this is a Rindler guy, and this is a Minkowski guy. So I just plug this into here. And so I get this equation. Okay, so this is all the Rindler precursor. Now let me do the Poincare precursor, again for this same ADS-Rindler mode. So now I want to use the Poincare smearing function. I switched over to Poincare instead of global because it's easier, but it's the same thing. And so it's easiest to use that if I have to apply that to Poincare modes. So let me now do a bulk Bogoliubov transformation. So I'm going to write B omega k Rindler in terms of the B omega k Poincare. So this is just the creation operator for Poincare mode. Here gamma is the bulk Bogoliubov coefficient, and the stated term here for the nu plus nu minus is because this equation is heuristically B omega k Rindler is B plus B dagger for the Poincare guys. Good. So this, now I use the Poincare precursor, so it's the same equation as this, but everything for Poincare. Nu plus, nu minus. And so now I need to show that this expression is the same as this expression. And so what that requires is that there's a relation between the bulk Bogoliubov coefficients and the boundary Bogoliubov coefficients. So I need this to be true. And these other modes, the ones with nu plus, nu minus less than 0, gauge freedom took care of those because they're gauge equivalent to 0. So it turns out this is true. And so I'm done. Which is slightly surprising. So this is the Bogoliubov coefficient transformation in the bulk between an ADS Rindler mode and a Poincare mode, and this is a product of an ADS of a Rindler-Minkowski Bogoliubov coefficients. Since this is true, then
why is it slightly surprising given the logic of your eloquent thought?
It seemed that this showing that these two things were equal required something non-trivial to happen.
Bogoliubov transformations are usually linear things somehow, quadratic.
I was also surprised that this relation holds.
It reminds me of how the gray body factor factorizes into left-moving and right-moving ones. And the gray body factor is a piece of a Bogoliubov coefficient.
Yeah, so since we needed this to be true, so we needed to show it some other way. So the way we did it is, usually you compute a Bogoliubov coefficient by computing the correct way to do it would be to compute on a space-like surface the overlap between an ADS Rindler mode and a Poincare mode. So that's kind of hard. So instead we did the overlap on a time-like surface, which we took to be the boundary. And then this immediately followed. And there's probably some reason why this is justified. Aside from the fact that we gave the answer that we wanted. Okay, let me list a couple of conclusions. I guess I'm done. So the thing we would like to conclude is that what we've shown is that freedom in radial evolution is this property of PDEs of the wave equation, that there are many different ways of evolving sideways, which corresponds to the fact that there are many different regions on the boundary in which you can use, whose data you can use to reconstruct the same bulk point. This dynamical freedom, this property of PDEs, is equivalent, or not really equivalent, but maps onto gauge freedom. At least a subset of gauge freedom.
Is freedom with all the arrows?
I don't know.
So if I were to, if the boundary theory is not a gauge theory, then what do I do?
I'm not sure. So I'm not sure what you would do. There would need to be some reason why these two things are equal. Without the actual model, I can't see what it would be. There's some other reason, at least to me, that it seems that somehow a gauge theory or something like it seems important, in that it seems important to have the theory to have operators which are truly non-local. Because, sort of for the obvious reason that all the local CFT operators, those are just dual to the local fields near the boundary, and we need something that's dual to local fields deep in the bulk. So we need something that's truly non-local.
Why couldn't I have a spin chain and I have an operator which is the product of spins on many sides?
So, indeed. Like you could say, like the Wilson line or Wilson loop one has in a gauge theory. You can just take some scalar theory and just take the exponential of phi integrated, perhaps, and that also looks non-local, even though it's a product of local operators. Somehow it
Well, in some sense, the Wilson loop is local because it's local in the transverse direction. You really want something fully non-local in all directions.
That's true. So now you've essentially made my points 2 and 3, so let me just write them down. So I guess point 2 is going to be that the thing that we learned from bulk causality, at least in this context, is that there are lots of CFT operators, which would have been surprising otherwise, at least to me. Lots of CFT operators, the precursors that commute with all the local operators, or essentially all.
You learned that as an operator equation?
Yeah, I think so.
I thought we agreed that we were just studying a small set of the states.
So I think this depends on what you're calling. So in this program, one will expand, right, the bulk field in terms of CFT operators perturbatively, say OO is 1 over n squared, K, OO, etc.
You're worried about the 1 over n, right? The 1 over n correction.
Yeah. So I mean, Ben.
Or the nature of the states.
Yeah, good.
Well, Ben suggested there are states where the 1 over n corrections are not small, which is
right.
Which I would have said too.
That's good.
Those states.
It's an up. Good. So it depends if you want to call this an operator statement or not. It's an operator statement on the subspace of the Hilbert space.
For which it's true.
For which it's
which could be called the code subspace.
The gist of your talk was that it was supposed to be true in the gauge invariant subspace.
Yeah. Once we've got another subspace, I don't see why.
No, but it's not a new.
Two subspaces.
I think the difference is what you're calling a code subspace is, to me, seems to be just the subspace where we always knew the precursors are valid, sort of the space
I'm
which
happy
is.
to be trivially right.
No, well, I think you're wrong. Let me get to that. So there's this property that needs to be explained, that you can represent the bulk operator here in terms of an operator with support here or an operator with support here. I think your statement was we don't have to explain this once we realize the fact that this doesn't hold as a full operator statement because we can put a big black hole and then we've left the space. However, even if you put your big black hole, this code subspace, which is as the low energy states, consider an operator here. Let me draw this a little bigger. We still need to understand, we can represent it in terms of an operator with support here, or an operator with support here.
Yeah, so I had that.
So why are those equal?
Yeah, so I still had that right in the model. I mean, even if I put a big black hole in the center, if I looked at the guys that were outside the black hole, I could still push them in different ways. It's just in this setting, you shouldn't just describe the code subspace as low energy states. So for me, there wasn't one code subspace. I could pick my subspace and then study the correction properties based on the subspace. So with that big black hole there, then we'd be talking about a different subspace, but it still would have this property.
But the subspace you're using depends on the bulk point of interest. For instance, for this bulk point, the perturbative.
That's okay.
Okay, well then what you're calling the subspace is just.
No, I didn't say that. So that's why I say a subspace. I mean, I don't want to say that there's only one that's interesting. I mean, lots of subspaces are interesting. Different questions.
Okay, so your subspace, if I understand, is just the space for which you can resum the perturbation. So we could say there are two different backgrounds. We'll call these two backgrounds perturbatively connected. If you can do the precursor expansion around each background and resum the perturbation series to show that they're equal, and that's what we'll call the subspace.
You could say the subspace is where the black hole isn't too big, for example, would explain this.
But that's not. It depends on the bulk point.
Could we imagine that there's some that there are both types of operators? There are some operators that you can define that really only make sense on the code subspace, and there's no statement about them being equal.
definition of the code subspace?
Well, there are many.
Let me finish the comment. And you could imagine there are other types of operators. Like for the type of operators, like the type that Daniel was describing, where you go in 10 meters from the boundary, and clearly, in a sufficiently excited state, and that's not going to make sense. But you could imagine that there are other types of operators that are smart enough to avoid falling into black holes, and that really for these types of operators there could be relations that are exact on the Hilbert space. I mean, maybe your operator here that's sort of pulling back, you could imagine that's pulling back out to the boundary when you put the black hole there, so that again there's an exact operator statement.
But yeah, I see what you mean. But I guess I was saying something. Well, I see what you mean. I was just making the point that if we're considering the bulk, if we're considering the bulk point here, then for this bulk point in this background, we don't need some of these relations to hold since we can't get this perturbability from the vacuum, but the bulk point here we can. But there's also, I mean, I'm not seeing the real relevance of low energy states.
I have a proposal, since we should finish by
sure.
cookie time. Why don't we let you finish your main points, and then we'll continue this in the discussion, which, by the way, is in the small seminar room at 3:30.
Okay, I was almost done concluding something. I guess the last point I wanted to make is so what seemed nice about this model is we could actually find the precursors, and what we found is this nice relation, which I erased, that this one, that a bulk particle is dual to the superposition of two boundary particles. So all of this was at leading order in 1/n, and so it seems natural to go to next order in 1/n. So if we go to next order in 1/n, this should still be doable in this model. We should probably make this a local gauge theory. The commutator with the electric field is 1/n suppressed, so it'll show up at this order. And it would seem interesting to construct this order alpha to the 4th correction to this, if that's what it is.
Why do you need to make it a local gauge theory at the next order?
Well, I don't have to, but since the real theory is a local gauge theory, it seems natural to use a model which is a local gauge theory. And in this model, I could have made it a local gauge theory and not really change what I'm saying, because the commutator with the electric field is 1/n suppressed, which is why I could ignore it.
Well, I mean, in the Chern-Simons example, you have another parameter k. You take that k much bigger than.
Yeah, sure.
Then
I guess I just said local because I wanted to get closer.
This is 1 + 1 dimensions, right? So you don't have.
Sorry, yeah. Sorry, yes. Well, it should be simpler.
Should be what?
Sorry, I agree. Thinking.
But none of this is really. It seems that there's a major problem which there hasn't been much progress, which is that we don't know how to construct the precursors in the real example, in the real case. This case of strong coupling, and it looks qualitatively different from this. It won't just be a bilocal, it will be space filling. And so it seems like it would be very useful to know something about what it looks like. Yeah?
You say the real case is n = 4?
Yeah. N = 4, or just something that's strongly coupled. And the precursor, and when you evolve it to a single time, you get something that's extremely non-local, not just these.
So even in this model, let's say you follow your nose and trying to construct the local bulk. Can you construct a precursor at one point in the bulk, another point in the bulk, and try to compute the commutator and try to see how small you can make it?
Yeah.
The 1/n expansion might fail to.
Yeah. This would be the idea. So the idea was that the 1/n term, we could still do this exactly. I mean, up to this order, and then starting from 1/n squared, maybe one would have a slightly smeared bulk field, or simply try to get this point and this point to commute as fast as possible.
Right.
Exactly.
One would try to implement what Dan was saying.
Yeah, exactly.
Commutators as small as possible.
That's right. That's what we started trying to do. Yeah.
Right.
That's right. And here it would be very honest because we really don't know But the bulk equation's in motion, so we won't be able to achieve it. All right, thank you.
Any short questions with short answers?
Yes.
Can you extend this to higher dimensions? Just the identity you need? Does it?
I think so, but we haven't tried. It's just a little harder. I mean, it's still easy to do the evolution on the boundary because it's still free. But the equation won't be as nice, but it doesn't.
Anything else short? Okay, well, we'll meet at 3:30 again. Thanks again.